Alrighty, folks. So we are headed now into Unit B Dynamics. So we are in Chapter 3. Again, you know the drill by now. Make sure you're following along with the notes, whether that's printing out to take them or following along on loose leaf. Just want to make sure we're actively engaging to actually get the most that we can out of each lesson. All right, here we go. Unit B. So as you probably guessed from the name of the unit, Unit B is all about what we call dynamics, okay? And what is dynamics? What does that mean? Well, it's the study of forces and their effect on the motion of objects. So naturally, our next question is, okay, so then what is a force? What do we mean when we say a force? Well, a force is nothing more than a push or a pull. It's just something that can act on an object to change its motion. I mean, you can try it right now yourself, right? Look at something around you, maybe your calculator or your pencil. Right now, it's probably sitting still on your desk. If you want to change that, what do you need to do? You need to reach out and, well, push it or pull it or lift it, apply some force to it in order to change its motion. And change is the key word there. A force can act on an object to change its motion. Okay? Forces are vectors. They do direction matters, right? Again, we can think about, the test if something's a vector. If you do something the same amount but in the opposite direction, does it cancel out, right? And for forces, it does, right? If you push your calculator to the right while at the same time pushing it hard just as hard to the left, right? The calculator doesn't go anywhere. Your two forces cancel each other out and the total force on your calculator is 0. And so it doesn't change its motion. It doesn't accelerate, okay? So force is definitely a vector. Direction matters. Okay, so just to really quickly, simply visualize this idea of a force, we'll come back to this a couple times today, but just as an intro, I'm going to turn it down to no friction for now. Look, we've got a box here that's not moving, right? How could we change that? Well, we'd need to apply a force. Forces can cause changes in motion. So if I push the box to the right, look what happens. Okay, it's getting faster and faster and faster to the right the whole time I'm applying that force. Forces cause changes in motion. Now, if I stop pushing it and just let it glide, notice it continues to move how it was before, right? There's no force on it now, and so there's no change in its motion. It's still moving, but it's not getting faster, slowing down, or changing direction, okay? If I want to cause a change in its motion, I could apply another force, right? I could come back and now push it this way. And look, I'm causing it to slow down. That is a change in its motion. If I keep pushing, right, I can even cause a change in it, continue to cause the change in motion. And now it's actually accelerating to the left, right? If I let it go, no force, it continues to move as it was before. We're going to explore this a lot today. We're seeing a good example right now of Newton's first law in action. Okay, if I melt that ice so that there now is more friction, right? Friction is a force and it causes a change in the box's motion. In this case, slows it down until it comes to a stop. Once it's stopped, there's no more friction because it's not moving. And so it sits there, right? No change in motion because no force. So that's all a force is, right? It's a push or a pull that can cause something's motion to change. Now, there are many different types of forces, but that's all they are. They all do the same thing, a push or a pull, okay? So just to kind of introduce you to a few different types of forces that you're going to encounter in this unit, okay? The first is kind of a general term, an applied force. That's kind of what we were just looking at in that simulation, right? It's just a general term we use to say, yeah, something is actually pushing this object. So a force applied by an outside source, maybe it's a machine, a human, whatever, right? To draw a quick diagram to visualize, maybe this person is pushing this cart to the right. We could call their force the force applied. The name is not super important, right? A force is a force is a force. They're all the same in terms of the math and the physics going on, but we'll be dealing with multiple ones, so sometimes we like to give them labeling, right? An applied force could be a good label for this. They're applying a force to the cart. Another force we'll have to think about a lot is the gravitational force. Okay, in other words, we call that weight. We'll talk a little bit about the difference between weight and mass in a moment here, okay? But weight, that's what you feel pulling you down to the earth, right? When you drop your calculator, its motion changes. If you hold it out and then drop it, that's clearly a change in its motion as it accelerates down towards the earth, right? Well, now we know that if something's motion is changing, a force must be causing that. Well, that in that case would be the gravitational force. Okay, so this is the force exerted on an object because of gravity, and it's always towards Earth, or if we're on another planet, right, towards that planet. So to draw a quick little diagram, pretty simple here, maybe we've got like an apple, and there's the Earth down there. It will feel a downward force, right? We call that Fg for the force of gravity, just a little subscript G. Okay, next up, frictional force. We saw that in the animation as well. Okay, so friction is a force that's automatically created between two surfaces that are moving past each other. Okay, you can feel it right now by, rubbing your hand across your leg or something like that. You can feel that there's some resistance there, right? That resistance is a force. It's resisting how you are trying to move. So friction always works against motion. Whatever way the two objects are moving, friction is resisting that motion. So if you slide your calculator to the right, friction is resisting to the left. If you slide your calculator across the table to the left, friction is now resisting to the right. So say we've got some box that's sliding to the right, its velocity is to the right. Well, between the box and whatever surface it's on, there's going to be friction resisting that, right? There's going to be a force of friction that resists it. And if we're not actively pushing this box with something, eventually that friction is going to change its motion and bring it to a stop, right? If you try sliding your calculator across the table, it's not going to go forever. That's because friction is the force slowing it down, resisting that motion that it has. Okay, next up, tension, the force of tension, or Ft. Okay, now really all this it's the force created in something connecting two objects, right? It's really just whenever we have like a rope or a string or something like that involved, the force is transferred from one object to another through the rope, and we call that tension. So let's just say I'm pulling a box, but now they're attached. I'm pulling it by a rope, okay? If I'm pulling it by a rope, then it's the tension in the rope that is actually, it's essentially transferring the force from me to the box, okay? We'll see tension today when we look at things hanging up. Tension sometimes in a rope might be fighting gravity, for example, if you're hanging something by a rope. Okay, again, these are all just forces. They're just different types of forces, but they're all the same thing, pushes or pulls. Just to draw another example here, right? Say we're hanging a bucket from a string, right? It's got its force of gravity that's trying to pull it down to earth, but that's being canceled out by the tension in the rope pulling it back up, right? So those two, since force is a vector, those two forces cancel each other out. So overall, we don't have a force, and that's why our bucket is able to stay hanging without its motion changing, without accelerating. Okay, next up, the normal force, sometimes also referred to as a contact force, which is kind of a good name because it gives us an idea of when we see it. It's whenever two objects are in contact, there's going to be a perpendicular force exerted on those objects by each other. So, take a look at, your calculator sitting on the table right now. You know that the force of gravity is trying to pull it down, but it's not accelerating down. Right? So there must be some upward force canceling that out. And we can see that, it's the table exerting a normal force upwards on it. So if I have some object sitting on a table, let's say an apple, there is a force of gravity pulling it down, okay? But the reason it's not accelerating down is that these two are in contact. The apple is in contact with the table. And so there's a normal force from the contact there pushing up just as hard. Right? Now, important note, normal, you might be wondering, why do we call that the normal force? What's like regular about that? Normal actually doesn't mean like usual or regular in this context. Normal is a mathematical term that means perpendicular at 90-degree angles. Okay, if two things are normal to each other, they make a 90-degree angle. So the normal, what's perpendicular here, is that the normal force is always perpendicular to the surface at the point of contact, right? So to show you a couple other examples, it's not always just something sitting flat. Let's say you're leaning against a wall, right? You don't fall through the wall, so we know there's some force there holding you up. Well, that's the normal force where you're making contact with the wall. The normal force is there to support you. Now notice, what angle does the normal force make with the wall? It's 90 degrees. It's perpendicular, right? For another example, let's think about, parking on a hill. The car's wheels are in contact with the surface of the road here, right? The hill. And so there will be a normal force, a contact force, where it's making contact. We could say 2 here, 1 for each wheel, right? I guess 4 if we could see this in 3D and see all 4 wheels, right? But it's a normal force. It's a contact force. And again, look at that angle, 90-degree angle. So that's what normal means. Normal means perpendicular. And it's always just perpendicular to the surface at the point where contact is being made between the two objects. And another force we'll see in Physics 20, a little bit more in Unit C and D, but it can pop up in Unit B as well, is the spring force. Okay, now this is just the force that is involved whenever we stretch or compress a spring, right? So if you've ever stretched out a spring, it wants to pull back to its original shape. That's the spring force in action. So if I were to take a relaxed spring and then squish it down with a mass, the spring is going to be pushing back up, trying to stretch back out on our mass, right? And hey, what caused it to squish down in the first place? It would be that force of gravity, okay? So forces, again, all different types here, or different origins, so to speak, but they're all the same thing. They're pushes or pulls that can act on an object to change its motion. Okay, now these next ideas here, as we start to explore them, I cannot emphasize enough how important these 3 very simple but very important ideas are, okay? I don't think it would be exaggerating to say these are the 3 most important ideas in physics, certainly in Physics 20, I would say, okay? And they are known as Newton's 3 laws of motion. Okay, named for Isaac Newton, one of, if not the most brilliant physicists of all time. It's hard to put into words how much Newton's work with these 3 laws, and all of his other work as well, changed the game when it came to thinking about our universe and how things work, okay? So these 3 laws, again, they're quite simple, okay? But they really tell us all we need to know about forces and their effect on motion, okay? So we're going to do the first 2 laws right away because they are essential for even beginning to think about forces and their effect on motion. So we're going to cover the first 2 right off the bat, and then we'll spend most of the lesson looking at examples of the first law, okay? The third law, while still important, it's not as essential for even starting to think about this stuff, okay? So that'll come up in the future lesson. But let's start here, okay? We're going to introduce the first and the second laws of motion. They're actually fairly closely related to each other. So here is Newton's first law. Okay, I'm going to write it out simply and then we'll elaborate on it a bit first. All it is this. If F net equals 0, F net is the net force, the total force acting on the object. Okay, if the total of the forces acting on the object is 0 newtons are the unit we use to measure force because Newton did so much work on it, we named the unit after it. Okay. If F net equals 0 newtons, then the acceleration of the object will be 0 meters per second squared. That's it. So all we're saying there is that an object will not accelerate. Its velocity will not change if there's no net force acting on it. Here's how Newton worded that. This is the formal statement of Newton's first law, okay? An object at rest or in uniform motion, so remember that's motion with a constant velocity, okay, will remain that way if no unbalanced force acts on it, or forces act on it. Okay. So stated, a little bit simpler, what we're saying there is that objects will not accelerate. Their velocity won't change if there's no net force applied to them. And an important reminder, right? Net force, no net force, doesn't necessarily mean there's no forces at all acting on it, right? I mean, look at you right now sitting in your chair. There are forces acting on you. Gravity is pulling you downwards, right? But it's being canceled out by the normal force in your chair pushing you upwards, right? Your calculator rests on your table even though there are forces acting on it because all of those forces add together to cancel. So remember, F net is not just a force, it's the net force. It's the vector sum of all the forces acting on an object. So in the previous unit, we called it the resultant. It's actually the same thing. It's just we use the terminology net force more when we're talking about forces. Honestly, don't ask me why. It's like F resultant. It's just kind of, I guess, habit that we call it the net force instead of F resultant. Whoops, I spelt resultant wrong. Okay, so all Newton's first law really says is that objects won't change how they're moving unless some unbalanced net force causes them to. Right? Objects like to keep doing what they're doing. They have what we call inertia. So this is sometimes called the law of inertia. And inertia is a concept of just resistance to change. So objects won't change how they're moving unless a force causes them to. So if you take a look on the back of your formula sheet, you will see physics principle 0 for uniform motion. And notice it's talking about, well, that is when the net force is 0. So in physics, this is always my advice to students, you start with very simple ideas and then you break them down and get, more specific to the situation you're dealing with. If you're dealing with a situation where you know that the object is not accelerating, it might be moving, but it's not changing how it's moving, okay, then you know that the net force acting on it is 0. Okay, so for example, if we wanted to figure out the normal force in this example here, right, we might not know what it is, but we know that it has to be just as big as the force of gravity because we know they have to cancel each other out, right? We would say Fg plus Fn equals 0, and from there we could start analyzing. So this is what we do when we know an object is not accelerating. We can say F net has to be 0. Okay, so that is physics principle number 0 on the back of your formula sheet. So let's look at Newton's first law in action a little bit here. Okay, are you ready for the most mind-blowing thing you've ever seen? Ready? We're going to watch this box and we're going to see how its motion changes if we don't apply a net force to it. Whoa, it's not changing. Right? There's no net force acting on it. This is an object at rest, so it's going to continue to stay at rest. Newton's first law, right? Okay, I'm just going to turn down friction so that there's no friction, hypothetically, okay? I'm going to get it moving, so I need a force to cause it to accelerate. Whoops, there we go. I need a force to cause it to accelerate, but now I'm going to take that force away. Okay, so now we have an object in uniform motion. Right? Okay, but there's no net force acting on it. So what does it do? It continues to move with the same motion. It has uniform motion. So students are usually pretty okay at first with the idea of, okay, if something is at rest and there's then there must be no net force acting on it, right? But keep in mind, if something is moving, it can still be moving without accelerating, right? In this case, it is moving, but it's not changing how it's moving because there is no net force acting on it. So it will continue to move at this velocity with uniform motion. It's not speeding up, it's not slowing down, it's not changing direction. To make it do any of those things, we would need an unbalanced force, right? Now I can slow it down. But as soon as I take that force away, it continues to move how it was moving. So objects at rest or in uniform motion will remain that way unless an unbalanced force acts on them to change that. So that's a very important distinction, and it's one students sometimes at first get a little mixed up on, okay? Forces don't necessarily cause motion, okay? Net forces cause changes in motion. But as we can see here, something can be moving with no force at all acting on it. And again, even when there are multiple forces acting on an object like we see here, they can cancel each other out so that the net force is 0, right? So look how this object is moving. It's still moving with uniform motion, even though we're pushing it. because the force of friction is pushing just as hard in the opposite direction. So that total, the net force on the object is 0 newtons, and therefore the acceleration is 0 meters per second squared. Okay, so I have linked a video in the description that talks about Newton's first law and gives a lot of good examples. I want you to pause the video, click on that link and watch that video. It is a very cheesy video, I apologize, but it does do a really good job of explaining it. Sometimes those old cheesy videos are the best ones, okay? So go ahead and watch that, then we'll dive into Newton's second law, which is very closely related to Newton's first law. Okay, so Newton's first law, again, just says that an object won't accelerate if the net force on it is 0. Here's what Newton's second law says. An object will accelerate if the force acting on it is not 0, right? If there's a net force, the object will accelerate. And it says a little bit more than that. It talks about how that acceleration depends on the force. So I'm going to say it nice and simple at first. We will dive into this in a second. But here is Newton's second law. It really boils down to an equation. The acceleration of an object will be equal to the net total force acting on it divided by the object's mass. That's it. That's Newton's second law, really. Now notice that Newton's second law really gives us Newton's first law. Right? If I put in 0 for the net force, what acceleration am I going to get as my answer? 0, right? So yes, this equation, we often use it with Newton's second law, but it's also the equation for Newton's first law, right? If I put in 0 for the net force, I see that the acceleration must be 0, okay? So Newton's second law says that, first of all, that an object will accelerate if there's a net force acting on it, okay, which we can see from this equation. If this isn't 0, there's no way for the acceleration to be 0, right? But it says a little more than that. It tells us about how that acceleration depends on the force and the mass. So we would say that the acceleration will be directly proportional to the net force. Now, directly proportional, what does that mean? A direct relationship just means that when one gets bigger, the other gets bigger too. So a bigger force causes a bigger acceleration. Hey, guess what? You knew Newton's second law before you ever took Physics 20. You did, right? If you want to change something's motion more, how do you need to push it? Harder or less hard? Harder, right? Exactly. We all know Newton's second law from a very young age, even if we've never worded it like this, right? To get a bigger change in motion, you need to push something harder. So a bigger F net results in a bigger acceleration. They are directly proportional. Larger force causes a larger acceleration. Proportionality, by the way, we show like this. We use this symbol. It just means acceleration isn't equal to force, but it depends on force like this. You'll see what it looks like when something is inversely proportional in the next statement here. Okay, so that is that. Well, we can see acceleration depends on two things, right? The net force and the mass. So again, you've known this for a long time. If something is bigger, let's say, a truck versus a bicycle, okay, do you have to push the truck harder or less hard in order to cause the same acceleration than the bicycle, right? If something's bigger, you need to push it harder if you want to cause the same change in motion, right? So the bigger the mass, the smaller the acceleration if you push them the same amount, okay? So stated formally, that is that the acceleration is inversely proportional to the mass of the object. So inversely proportional just means when one is bigger, the other is smaller. So when we have a larger mass, we actually get a smaller acceleration. And again, you knew this. If you push a truck just as hard as you push a bike, the bike is going to accelerate a lot more because it has less mass, right? So to show that, we would say the acceleration, again, this just means it's not exactly equal to, but here is how it depends on the mass, right? Inversely proportional. As this gets bigger, this is actually going to get smaller. Makes sense because we're dividing by the mass, right? If I put a bigger number here, I'm dividing by a bigger number, I'm going to get a smaller answer for my acceleration, right? And vice versa for the net force, that's up top. If I put a bigger number in the numerator, I get a larger answer as a result. So this is basically, folks, the only equation you need for Unit B, more or less, right? This is the guiding starting point for every single problem we're going to solve in Unit B. We're going to say that the acceleration is equal to F net over mass, or F net equals ma, rearranged a bit, right? We're going to apply that in a lot of different ways, but that's the idea guiding us throughout. The net force acting on an object, if we add up all of the forces, it has to equal the object's mass times its acceleration. If it's not accelerating, then we're dealing with Newton's first law, and this is just zero, right? F net equals ma. So on your formula sheet, you can see this is numbered as, well, physics principle number 1. It's accelerated motion, and that's what happens when the net force acting on an object is not zero. If the net force is not zero, the object will accelerate. Physics principle number 1. Okay, so let's explore Newton's second law here a bit visually. If I apply a force of 50 newtons, right now there's no friction, so we know that it will accelerate. And sure enough, its velocity is changing, right? It's accelerating. It's not accelerating super quickly, but it definitely is accelerating. Okay, now let's try this again with a larger net force. So our box is getting faster and faster and faster. Okay, but let's do it again with a larger net force. So again, I'm going to do no friction, okay, but I'm going to make the applied force now very big so that there's a large net force. And look at that, right? It accelerates like it did before, but now it accelerates a lot faster. Acceleration is directly proportional to the net force. So a larger force causes a faster acceleration. Okay, now let's explore the mass part of this. Okay, so I'm going to push with a force of 150 newtons. There's no friction, so that's just my net force. And again, it accelerates, right? It gets faster and faster and faster and faster and faster. Okay, let's now replace that box with something that has more mass. Okay, so I've paused time right now. I'm going to press play in a second, but just letting you get your bearings here, right? I'm applying the same net force, 150 newtons, no friction, so that's just our net force. But now we've got a box, a refrigerator, and a man sitting on top of it all, so the mass has gotten much bigger. How do you think that will affect the object's acceleration? Let's see. Aha, so still accelerating because there is still a net force. You'll notice it's getting faster and faster and faster, but it's doing so much more slowly, right? The velocity is constantly changing, but it's changing by a lot less than it was when we just had the box, right? We can see that in real time. If I make the mass smaller again, look at how the acceleration picks up, okay? So there is both of these ideas in action. Bigger force, bigger acceleration. Bigger mass, smaller acceleration. And all of that is rolled up nicely into this equation, okay? One more point that we should address here, the acceleration will also be in the same direction as the net force. Which makes sense, right? Because if you overall something is being pulled to the right, you would expect it to accelerate to the right, not to the left, okay? And so that idea is also contained in the equation because if F net has a sign, well, the acceleration is automatically going to have the same sign, right? Mass is a scalar. It doesn't get a sign, so they must be in the same direction. So there we go. We talked a lot about accelerations in Unit A, right? Changes in velocity, but we didn't get to really dig in and talk about why things' velocities would change in the first place. Well, now we know. It's because of Newton's second law. So when something was dropped in Unit A, and we talked about how it would accelerate because of gravity. Now we can go a step further and say because the force of gravity there is the net force if it's just falling, right? There's no other forces acting on it. And so it accelerates. Okay. Before we move on, I do just quickly want to talk about units as well, okay? So we know that the unit for force is a Newton, but that's actually not a base unit. It's what we call a derived unit. So remember, the base units are things like kilograms, meters, and seconds, okay? So we measure the force in newtons, but really we know that forces equal masses times accelerations, right? Well, masses are measured in kilograms, not grams, kilograms. That is the one unit in Physics 20 that's base form, has a prefix. So kilograms is the base unit of mass. Okay, and acceleration is meters per second squared. So what this is what I'm showing here is that a Newton is really a kilogram meter per second squared. In base units, this is how we measure forces. Okay. The reason we call them Newtons is honestly because we use them so much, right? We use them so much. We get sick of writing kilogram meter per second squared. And so we said, hey, can we just call these a Newton? Because we talk about forces so much. Okay. But in base units, it's a kilogram meter per second squared. Plus, we wanted to name something after Newton because he did so much, right? Okay. So that is a Newton. It is really a kilogram meter per second squared in base units. All right. Let's talk about weight versus mass. So weight and mass are not the same thing, okay? Can't stress that enough. It's a very common student misconception, and it's partly down to how we use them in our day-to-day life, right? We often do in our, everyday language, we say them like they mean the same thing, but they are not. Weight is a force. It is measured in newtons, okay? Specifically, it's the force of gravity. It's the force that you feel because of gravity. That is weight. So force of gravity is not the same thing as your mass. You feel a force of gravity because of the mass that you have. Okay? So mass is a measure of the amount of matter in an object. That's all it is. It's basically saying how much stuff is there in this thing, right? Objects with more mass have more stuff. They have more matter in them, okay? It's measured in kilograms, okay? Again, important to note, sorry if you're taking chemistry where you use grams, the base unit of mass is actually kilograms, not grams, okay? So mass is very closely related to the inertia of an object. We talked about inertia earlier, right? It's the object's resistance to change in motion. And we know that because, again, things with more mass, it's harder to change their motion. So things with more mass have more inertia. In fact, you can really look at mass and inertia as kind of being the same thing. Something has inertia because of its mass, okay? Now, weight, the force of gravity, Fg for short, is the gravitational force acting on an object because of the mass that it has, okay? So force of gravity is equal to mass times acceleration due to gravity. We're going to start using the symbol little g for acceleration due to gravity, okay? That's just good old 9.81 as long as we're on Earth, right? 9.81 meters per second squared towards the Earth or down. Okay, the reason we introduce a new symbol for acceleration due to gravity here instead of just calling it another A is honestly just because we use it so much and it's kind of a specific thing. So we're always just going to call acceleration due to gravity. We're going to use G. It's still an acceleration. It's just a specific acceleration being caused by, well, gravity. Okay, so this is, we know this is just F equals ma. Okay, but the A, the acceleration here, is the acceleration caused by gravity. So again, it's just Newton's second law, right? It's acceleration equals the acceleration that an object feels will be equal to the force causing it divided by mass. Well, what force causes acceleration due to gravity? The force of gravity, right? So G equals Fg over m. Rearrange this, we get Fg equals mass times acceleration due to gravity, right? The acceleration will be equal to the force causing that acceleration divided by the mass. For acceleration due to gravity, the force causing the acceleration is the force of gravity. So you see that equation here on your formula sheet, but it's really just this equation when the net force is the force of gravity. The force of gravity will be mass times 9.81 on Earth. Again, reminder, if you've forgotten that number, it is here on your formula sheet. Acceleration due to gravity is 9.81. By the way, this actually allows us to prove something we saw in Unit A. Remember how we saw that whether you drop a bowling ball or feathers, if the only force acting on them is gravity, right, there's no air resistance, they should take the same amount of time to hit the ground no matter what their mass is. This equation allows us to prove that. If something is in free fall and there's no air resistance, what's the net, the total force acting on them? Well, it would just be the force of gravity, right? The force of gravity pulling them down. But now we know that the force of gravity is just mass times acceleration due to gravity, right? So Fg is just m times g, acceleration due to gravity, but we're dividing that by the object's mass. So look at that. Mass over mass cancels out, and we see that no matter what that number was, the acceleration will be acceleration due to gravity. On Earth, 9.81. So pretty cool, right? We've just proven what we saw in Unit A, that no matter what an object's mass is, if it's in free fall, it's just falling because of gravity, it will take the same amount of time to fall because it has the same acceleration. Whether it's a very light object or a very heavy object, the masses cancel out, right? And really what's going on here is, yes, objects with a bigger mass do feel a bigger force of gravity, but they're also harder to accelerate because they have more mass. And so even though they feel a bigger force, that force doesn't make as big of a difference because they have a larger mass, and those two competing things end up canceling each other out perfectly so that all objects, regardless of their mass, fall at the same rate. Okay, so the force of gravity, in other words, the weight, is measured in newtons like any other force. It is not the same thing as mass. Okay, so let's explore this idea. What's the mass and the weight of a 10 kilogram bag of flour? We'll assume we're on Earth here. Well, mass is easy, right? They told us it. The mass is 10 kilograms. That's essentially a measure of how much matter there is in that bag of flour. It has 10 kilograms of mass. Now, weight is a force. It's the force of gravity. So like all other forces, it's equal to, right? A equals F net over M, or F net equals ma. So the force of gravity is equal to mass times acceleration. And the force of gravity, that's acceleration due to gravity, right? So Fg equals mg. Now we're talking vectors, we're talking forces. I'm actually going to find down as positive here. That might feel a little weird, but it's just because I know we're talking about downward stuff, so I'm going to leave it positive, okay? Well, that means that the force of gravity will be its mass, 10 kilograms, times the acceleration due to gravity. So 9.81 meters per second squared. And therefore, the force of gravity, the weight of this flour, the force it's feeling because of gravity, is going to be 98.1 kilogram meters per second squared, but that's a Newton, right? So 98.1 newtons, we got a positive, so its force of gravity is going to be downwards. So its mass is 10 kilograms on Earth, but the weight, the force of gravity that it feels because of that is 98.1 newtons, pulling it down to Earth. I'm not technically doing my sig digs right there, sorry, but I'm just leaving it like that for the sake of comparison. Okay, now, what is the mass and weight of the same bag of flour if we go to the moon? Well, has the flour's mass changed? Is the amount of stuff that is contained within that bag of flour, is that any different if we take it to the moon? No, it's not. Its mass is the same, right? Nothing has changed about how much flour we have. What will have changed is the force that it feels on the moon because of that mass. So it still has 10 kilograms of mass, but it's going to feel a different force of gravity as a result, because acceleration due to gravity on the moon is different than acceleration due to gravity on Earth. We can see here it's saying its g moon is 0.16 times g Earth. So there's 16% as strong of a pull on the moon as there is on Earth. In chapter 4, we'll explore a little bit about why that's the case. But for now, same equation, F equals ma. So for gravity, the force of gravity equals the object's mass times acceleration due to gravity. Its mass is still 10 kilograms, but now on the moon, acceleration due to gravity is 0.16 times 9.81 meters per second squared, right? It's 0.16 times Earth's acceleration due to gravity. And so on the moon, it would only be feeling a force of, I'm getting 15.696 newtons of gravitational force pulling it downwards. Again, it's not like the mass of the flour changed, just the force of gravity it's feeling as a result. So to 2 sig digs, that would be 16 newtons, right? So notice, mass the same, weight very different on the moon versus Earth, because weight is a force. It's a push or a pull. Mass is a scalar. It's just how much stuff is there. Okay, let's try this one out. Okay, so the average weight, remember that's a force, the force of gravity, of a human on Earth is 687 newtons, right? So that is the force of gravity they feel on Earth. We're being asked, what is the mass of an average human? Well, again, this is just F net equals mass times acceleration from your formula sheet, right? But for gravity specifically, we know that the acceleration is acceleration due to gravity, right? That's the acceleration that the force of gravity would cause on its own. So Fg equals mg. We're going to use that idea a lot, okay? We want to figure out the mass. Well, right now, mass is being multiplied by g, so divide both sides by g. And we get that their mass will be equal to the force of gravity divided by g, acceleration due to gravity, right? We're on Earth, so g is just 9.81. I'm doing a really bad job of showing my work top to bottom here, sorry. But we can go ahead and plug in our numbers. So the mass is going to equal the force of gravity, 687 newtons, divided by acceleration due to gravity, 9.81 meters per second squared. And doing that, I get that the mass is 70.0306. Now, units. We know mass should be kilograms, but let's not forget, unit analysis here. A new unit kind of for us to be thinking about is newtons. So why should we just trust that this comes out to kilograms? Let's do a quick little unit check to make sure. So essentially what we're trying to do, we know that a mass should be in kilograms. Square brackets are kind of the way we show that we're just thinking about units here. Is a kilogram equal to a newton divided by a meter per second squared? If so, we know that our algebra checks out, right? If not, we know something went wrong. Well, remember, a newton in base units, since F equals ma, right? A newton is really a kilogram meter per second squared. We're dividing that by meters per second squared. And hey, look at that. Kilogram meter per second squared divided by meters per second squared. Well, we have meters per second squared divided by meters per second squared. Sure enough, a kilogram equals a kilogram. So at least our units are working out correctly, right? We feel pretty good about that. And that's why we can say here, yeah, we got a kilograms out, right? We're not just guessing that that would be our unit. That really is, we can show what our units would be. So the average mass of a human on Earth would be 70 kilograms. All right, so with forces, there's a new type of diagram we think about often with them. So we're just going to do a little tutorial on diagrams. A lot of this is going to be familiar territory. For example, we can draw representational diagrams. You're used to those. Those are just your little quick sketch to actually show what's going on, right? Helps you get your bearings and understand the situation. Now, the new type of diagram that we're going to look at is called a free body diagram, FBD for short, okay? And these are particular to, for now, forces. In Physics 30, you'll use them for fields a little bit too, okay? But for forces, what a free body diagram does is it just takes the situation and it simplifies it, right? Instead of drawing the full car, the car is just an object, so we're just going to draw it as one point. Okay, instead of, all these complicated pictures, we're just going to simplify because ultimately it's comes down to what forces are acting on this object. We just simplify the object down to a dot. We draw it as a little dot. And then we use arrows to show all of the forces that are acting on that point. Okay, so all of the tails are just going to come from one point on our vector arrows. You'll see it in action a lot on the next page here. And why do we want these? Well, again, it really just boils down to what's the total force acting on this object? What's going on? And so free body diagrams simplify all of those forces to just illustrate overall what's going on. How is it being pushed? How is it being pulled? And it sets us up for success when we go to analyze with the math. And then, hey, you know these, you love them, good old vector addition diagrams, right? Forces are vectors, and so we can draw VADs for them. They add just like any other vector, right? Tip to tail to add up all the forces, and then to find the net force, the resultant force, we go from where we started to where we ended. Tail of first to tip of last, and that gives us the resultant vector, which in the case of forces is what we call the net force, F net. So if, three people are all pushing on one object, one person's pushing it to the right, one person's pushing it up, and one person's pushing it off to the, off at an angle up and left, okay, then overall, the net force is going to look something like that, right? It's just the total force being applied to the object because of these three forces, from where we started our diagram to where we finished. So essentially, we could replace these three people pushing with just one force that looks like that, and the overall result would be the same. Okay, let's get some practice with these diagrams. We're going to focus especially on the free body because those are the new type, but this will also be good practice for reminding ourselves of VADs as well. So we're going to draw all three representational free body and vector addition diagrams for the following situations. Now, important, assume there is friction between the box and the surface in all scenarios where there could be. Okay, so first up, a box at rest on a flat surface. So we've got a box at rest. Now, the box has mass, so it does feel a force of gravity pulling it downwards. But it doesn't accelerate. How come? Right, there's a normal force there canceling out our force of gravity, right? We know that if nothing was challenging this force, it should be accelerating downwards. But since it's in contact with the surface, there's a normal force pushing up just as hard. Okay, free body diagram. Here's what we're going to do. This is great, gives us a good idea, but as situations get more complex, there can be a lot going on. So what we're going to do for a free body diagram is we're going to take this box and we're going to say ultimately it's just an object and we're interested in all of the forces acting on it. So let's just simplify and draw the box as a dot. And now we just think about all the different ways that this box is being pushed or pulled, right? Well, the force of gravity is pulling it downwards, okay? But we know that can't be the only force because the box isn't accelerating. The normal force is pushing up on it just as hard. And there we go. There's our free body diagram. Notice how it just kind of gives us a way to quickly visualize overall what kind of things are pushing and pulling on our object. Now for our VAD, same as always, we're going to add these two force vectors, tip to tail. Okay, now we can make a prediction here. We know that our box is not accelerating. So what does that mean we know about the net force? Right, it needs to be zero. Newton's first law. If this box is at rest, it's not changing its motion, okay? Well, then the total force acting on it needs to be zero. So as big as Fg is pulling it down, tip to tail, the normal force is pushing it up. And so overall, what's our net force? Well, we finished our diagram where we started it, right? There is no net force to draw in because as we would expect, F net is zero. It's not accelerating. Okay, a box moving with uniform motion on a flat surface. So pause right away. If it's moving with uniform motion, is it accelerating? No, it's not, right? Okay, so if it's not accelerating, what's the net force acting on it? Zero. You've got it. If it's not accelerating, which it's not, if it's moving with uniform motion, then the net force on it must be zero. No way around that. So we have a box that is moving, okay? It does have a velocity, okay? But it's continuing to move in the same way. Now, it says assume there is friction where there could be. Well, when two objects move past each other, there is friction between them. So there would be here a force of friction resisting the motion. Okay? Now, can that be the only force acting on our box? Can that be it? Right. No, it can't be the only force. Otherwise, it would be accelerating, right? It would be, in this case, getting slower and slower. So there must be some other force canceling out that force of friction. Maybe it's somebody pushing it, right? Maybe it's somebody pushing it forwards. Whoa, they've got long arms, okay? But we know if it were just friction, this box would be getting slower and slower. It wouldn't be uniform motion, okay? Oops, I drew it a little too big there. There we go, right? Again, that's not some magic thing that I just pulled out of nowhere, right? I knew that there had to be a force just as big as friction, but in the opposite direction because of the uniform motion. The acceleration is zero, so there's no way around it. The net force has to be zero, right? For every force that's acting on it, there must be some other force or forces canceling it out. Okay, now, again, it still has mass, so it's still going to feel a force of gravity, right? But it's also not accelerating up or down, so we still have that normal force there canceling out our force of gravity. Okay, so see what I mean? As things get more complicated, this is great, but ultimately we're just interested in all of the ways this object is being pushed or pulled. So let's draw it in as just a dot, and then we can simplify a bit and really focus on what matters here. There's a normal force up, but then just as big but downwards is the force of gravity, and then they must be pushing it to maintain uniform motion, but if I stopped there, this object would be accelerating, right? So there must be something in the x-axis. In this case, we know it's friction pulling just as hard to the left, right? And so you can kind of see overall, now we can think about all the way those different forces are pushing and pulling and see that this thing should be overall net force balanced. Now we'll see that for sure on our VAD when we add these tip to tail, we're expecting to start our diagram where we finish it, right? Because the net force should be 0. So there should be no net force to draw in. So the order I draw them doesn't really matter. I'm just going to go around clockwise maybe. We've got our normal force upwards, tip to tail, our applied force to the right, okay? And then tip to tail, our force of gravity down. And look at that, right? Vertically, those two forces are canceling. Good, because it shouldn't be accelerating vertically. And now horizontally, our friction and applied force are canceling. So that overall, there is no net force to draw in, right? Our F net is 0, which we knew it had to be because it was moving with uniform motion. It's impossible to move with uniform motion if there's a net force acting on you. Okay, now a box speeding up when pushed on a flat surface. So pause once again. Is our acceleration 0 if it's speeding up? No, it is not, right? Our acceleration is not 0. This thing's velocity is changing. So what must be true about the net force? It cannot be 0 either. There must be some overall unbalanced force acting on this object. Okay, now we can do the FG and the FN, right? Vertically, it's not accelerating, but those forces are acting on it vertically, okay? What's a little more interesting here is the horizontal. We know there is friction. It said whenever there would be friction, we are going to assume there is friction, okay? So friction would be resisting that motion, but it's picking up speed. It's accelerating, right? So whatever force is fighting friction is winning, so to speak. So the applied force, should I draw it smaller than friction, bigger than friction, or the same size as friction? It needs to be bigger than friction, right? So that overall, we do have a net force acting on our box to the right. And that's what's causing it to accelerate, to pick up speed to the right. So for our free body diagram, we'll draw the box as just a dot. Vertically, not super interesting for now, okay? But we have our force of friction, right? Resisting motion. And then we know that our applied force has to be larger than that force of friction, right? And so now, again, you can see on the free body diagram by just stepping back and taking a look at this, we can kind of see, yeah, this thing should be accelerating. The forces aren't balancing each other out. One is kind of winning, so we should have an acceleration, okay? When we draw our VAD, we'll see that for sure. So tip to tail, I'm going to add the normal force and the applied force, and then the force of gravity, which I know has to be as big as the normal force, otherwise it would be accelerating up or down, which it's not, right? And now when I go to draw the force of friction, I know it's smaller than my applied force, right? Otherwise this box wouldn't be picking up speed. So I'm going to draw it smaller than my applied force. There's the force of friction. So now when we go to draw our net force, right, like always, our resultant vector from where we started our diagram to where we finished, look at that. Sure enough, there is a net force, right? It's not 0, and we knew it shouldn't be because it was accelerating. What's more, how we've set up our diagram, right, it should be accelerating to the right. Well, that requires a net force to the right. So some of FA cancels with all of FF, I guess, but we're still left with a bit of a net force to the right. And that's how this object is able to pick up speed to the right, to accelerate. Net forces always cause accelerations. Okay, and finally here we've got a box slowing down. So right away, good practice, just ask yourself for every question, is F net 0 or is F net not 0? If it's slowing down, is its velocity changing? Yes, right? So is it accelerating? Yes. So what is the net force on it? Well, it can't be zero, right? If something is accelerating, the net force acting on it cannot be zero. Okay, so let's say it was moving to the right, right? We've pushed it, but now it's been released. So it's kind of just gliding for now, right? Its velocity is this way, okay? But we've released it. So this person is no longer applying a force to it. It's just coasting, okay? So why is it slowing down? Well, it's moving. Whenever two objects move past each other, there is friction resisting that motion, right? So there is a force of friction there. And now there's no applied force to cancel that out. So in the x-axis, the net force is actually just going to be that force of friction, right? And so it will accelerate in the direction of friction. It's moving to the right, accelerating left. We know that means it's going to get slower. So for our free body diagram, again, vertically, normal and gravity are just canceling each other out. But horizontally now, here's all we've got going on. We've just got the force of friction, right? And a quick glance at that free body diagram tells us, okay, this thing should definitely be accelerating, right? Compare that to one of these ones where, yeah, they look like they're all kind of canceling each other out. Definitely we have a net force here. Let's see it with our VAD. We've got our normal force up, tip to tail, our force of friction to the left, and then downwards, tip to tail, we've got our force of gravity, okay? And we're done. Those are our three forces, so our net force should be from where we started to where we finished, right? The total force acting on this object is, like we predicted, to the left. So since it was moving to the right, but the net force acting on it was to the left, it accelerates to the left and therefore gets slower and slower and slower. Okay, so there's our little crash course / reminder of the different diagram types. Let's go ahead and now actually start calculating some stuff with our new diagrams in our back pocket. So Johnny has a mass of 35 kilograms and is sitting in a wagon with a mass of 15 kilograms. Mo pulls him to the left with 50 newtons of force, okay, while Ian pushes from behind also to the left with 45 newtons of force. The force of friction is 90 newtons. What is the net force acting on Johnny in the wagon, and which of Newton's laws applied? Okay, so let's go ahead and just draw a quick representational diagram. So we've got Johnny sitting in the wagon. Now careful here, the Ian and Mo and friction are pulling on the whole system here, right? The wagon and Johnny. So the mass is going to be 35 plus 15 or 50 kilograms. So that's the mass of our object here that we're dealing with. Now Mo pulls to the left with 50 newtons of force. So I'm going to call that Fm for Mo. Okay, the Mo's force is 50 newtons, while Ian pushes from behind. So I'm going to call that Fi for Ian, right? It's just a force. We can call it whatever we want. I'm going to call it Fi, and it's 45 newtons to the left. Now the force of friction is 90 newtons. So we have to think about this. Which way would friction be? Mo and Ian are trying to move Johnny to the left, right? Now, friction always resists motion. So if Johnny's at rest right now, they're trying to move it to the left. Friction is going to be fighting them to the right. Now, friction is 90 newtons. Okay, so it's bigger than Mo and it's bigger than Ian. You might be looking ahead a little bit and realizing, but it's not as big as both of them together, right? So I'm going to draw it in bigger than Mo, bigger than Ian. Okay, and then if you want to think about the y-axis, truthfully here, you could notice that it's a flat surface. We don't have any vertical forces, so we can just focus in the x-axis, but there's nothing wrong with saying the force of gravity down will be just as big as the normal force up, and therefore Johnny isn't flying up into the air or sinking into the ground, but he might accelerate horizontally. Okay, now see what I mean? Things can get kind of complex with our representational diagram, so it's nice to just simplify and say, great, but what's really going on in terms of the forces pushing and pulling on Johnny and the wagon? So we'll draw them as a dot. Vertically, those are just canceling each other out. But horizontally, we've got a bit more going on, right? There is the force of friction resisting them, And then together, there's Ian pushing to the left, and Mo just a little bit stronger, also pushing to the left. Okay? So we could see it's, it might be close to even. We're going to have to, properly draw our VAD and then do the math to really know. Okay, but let's do our VAD. So I'm going to just start at the normal force and go clockwise. Doesn't really matter what order. Normal force, tip to tail, let's add friction. And then the force of gravity. Now here's where we'll want to think a little bit, right? Mo is 50, Ian is 45. So when we go to draw these two together, well, 50 plus 45 is 95. So their combined force is actually a little bit stronger than friction. So I'm going to draw it just a little bit bigger than that friction force, right? Well, first let's do Ian. Ian is 45, so he's about exactly half of the 90 that friction is providing. But then Mo is 50, so he takes us just beyond. Okay, tip to tail, just adding them up like we would any other vector. So there we go. We've added up all the forces. To find the net force, well, we started here and we finished our diagram here. So our net force looks like it's going to be that, right? To the left. Not super big, but still a net force to the left. Okay, so we've got our prediction here now, right? We've drawn our 3 diagrams. We want to now actually calculate what is the net force acting on Johnny and the wagon. The net force is just the result of adding up all of the forces. Now we need to be super careful here. Forces are vectors. Direction matters. So I'm going to go ahead and before I start adding things, I'm going to make sure I've defined my directions and their signs. I'm going to call right positive and left negative. And I'm going to call up positive and down negative. And now we can see again in our y-axis, it's just going to be 0, right? But in our x-axis, something a little more interesting is going on. So F net, again, it's the sum of all forces acting on it, right? So what forces are acting on our object in the x-axis? Well, we've got Mo, Ian, and friction, right? That's it. That's all F net in the x-axis is. Add up all the forces in the x-axis. So Mo's force is 50 newtons to the left. Well, I'm calling left negative, so I'll say negative 50 newtons. Ian's is 45 newtons to the left, so add another negative 45. But then friction is 50 newtons to the right. So I'm going to say, friction is 90 newtons, not 50, plus positive 90 newtons. And if we add these all up, we get that the net force horizontally is going to be negative 5 newtons. So that negative means it's to the left, which makes sense. We knew that Mo and Ian together were 5 newtons stronger than friction, right? So the overall force should be to the left. So the net force is 5.0 newtons left to 2 significant digits, okay? And therefore, it asks us which of Newton's laws applies, first law or second law? It's the second law, right? F net is not 0. So Johnny and the wagon will accelerate. They'll accelerate to the left. It'll be a pretty small acceleration. 5 newtons is not a very big net force, but this would be Newton's second law. Because F net does not equal 0, right? Physics principle number 1 from our formula sheet, not number 0. Okay, let's try out another one here, and then it'll be your turn. So an 83.6 kilogram box must be moved to the northeast corner of a room along a frictionless surface. Okay. So sometimes we're told there's no friction, and that just is kind of a simplification that the problem makes for us. So 12 newtons are applied to the north and 18 newtons are applied to the east. Let's start drawing our diagram. So whenever we get northeast, southwest involved, right, we're going to need to look at this from above with a bird's eye view, okay? So 18 newtons are applied to the east. We'll call that F1, 18 newtons to the east, and then 12 newtons to the north. Okay, so notice they are in completely separate axes, right? We're not just going to add those two because we can only add x's to x's and y's to y's, right? Let's draw our free body diagram. Right, just simplifying the box down to a dot, drawing this one slightly bigger because 18 is bigger than 12. Okay, and for our vector addition diagram, we're going to draw these tip to tail to add them up, right? So here is F1, it's 18 newtons perfectly east, and here is F2, it's 12 newtons perfectly north. So overall, what's the net force acting on this object? Well, like always, to find the total vector, right, the net or resultant vector from where we started to where we finished, okay? And that's what we want to find, the resultant force, the net force, right? Again, it's saying if it's being pushed like this and like this at the same time, then overall, how is it being pushed, right? If we just pushed it with that force, it would be the same result as pushing with these two forces separately. So hang on a sec, does this look familiar, right? We know 18 newtons to the east, 12 newtons north, that's a 90-degree angle between east and north, right? So how could we figure out this side of our VAD? With the Pythagorean theorem, right? C squared equals A squared plus B squared. So F net squared is just going to equal F1 squared plus F2 squared. So F net is going to be the square root of, okay, F1 was 18 newtons and F2 was 12 newtons. So square those, add them, and then square root to get the magnitude of our net force. I'm getting that the magnitude of the force, how big it is 21.6333 newtons. Okay, now force is a vector, so we do need a direction, right? Now we know from Unit A, we can't just say, you know, northeast, somewhere between north and east, because there's lots of directions that are between north and east. We need to communicate this specific direction, and to do that, we're going to need an angle. So once again, like always, right, our VAD keeps coming in handy. We don't just draw it and forget about it. We can come back to it and see, aha, well, now I can see the angle that I'm looking for, right? The VAD shows me. If I can find that angle, I can use it along with north and east to describe what direction this vector is pointing, okay? So we technically have all three sides now, but I like to use the sides they gave us just because we're a little more confident in those. We have opposite and we have adjacent. What could we use? Tan, right. We could use that the tan of our angle is equal to the opposite side, 12 newtons, over the adjacent side, 18 newtons. But again, we don't want tan theta, we want theta itself. So take inverse tan of both sides, that's second tan on your calculator of that same ratio to get that theta is 34 degrees. Okay, so now we know that F net, that angle there is 34 degrees. Now we just need to be careful about describing it with the compass directions. We know we're somewhere between east and north, and we know F net is pointed like that, right? We just found this angle here based on our diagram setup. So make sure you're finding the correct angle here, right? This angle here is 34 degrees. So to describe that, we could say we are, right, from east, we went 34 degrees towards north. So we are 34 degrees north of east. So putting that all together to two significant digits, the net force acting on this box is 22 newtons at 34 degrees north of east. Right? And again, if you had drawn your diagram slightly differently, if you had gone like this, you'd still get the right answer. You would probably just find this angle, which would be east of north. So for you, you might say 56 degrees east of north. That's the same thing as 34 degrees north of east. You're just saying start at north and go 56 degrees towards the east, but you end up facing the same way. Okay, so all that vector stuff we did in Unit A still applies because forces are vectors, right? We're going to see that a lot throughout this unit. Okay, so go ahead and get some practice now. Pause the video and for sure do this one, okay? You want to get some practice here with the idea of calculating the net force acting on an object. But again, net force is just the result of adding all the forces up. Don't forget, you have to keep x's and y's separate. You can add x's to x's, you can add y's to y's, but you can't mix them. If you are wanting to take a little more time right now to practice before moving on, maybe you really want to get this stuff down before you continue, those are good ones to try at this stage too. So no matter what, make sure you do this one right now before moving on, okay? But if you'd like some extra practice now, you can try those, or as always, you can save them for after the lesson when you're doing all your practice in one big chunk. Okay. So as you've probably been starting to think about, right, forces are vectors, and so they can have components in both axes, right? And we need to treat those axes separately. We've seen a little bit of that, but let's remind ourselves when we have a vector that has components in both the y and the x-axis, how we deal with that. We did it a lot in Unit A. It's no different now, except now instead of a distance or a velocity, our vector is a force. So if we were to pull on this dog's leash, right, kind of uppy and righty, it has, well, two components in the x and the y axis. We are pulling it up and we are pulling it right? We could call that fx and fy. It's just the rightness and the upness of this force where we're pulling at an angle, okay? And so like all of the other vectors we've worked with, right? If a force acts at an angle, before we can do any real useful addition, right? The vector needs to be separated into its x and y components because we know we can only add x's to x's and y's to y's. It doesn't make sense to just say, you know, if this is 5 and this is 4, then this is 9, right? It doesn't work that way. We need to find that x component, find that y component, add them up separately to get the total x and the total y, and then we can use Pythagorean theorem to solve for the vector itself. So let's just remind ourselves, quick review, how do we separate vectors into components? It's all just trigonometry. So if we have a force of 60 newtons that's at 10 degrees from the horizontal, so what that means is, well, here's the horizontal, right? 0 degrees. We are 10 degrees from it. So we are applying a force of 60 newtons, but it's at an angle, right? And it is pulling it to the right while at the same time pulling it up, right? We can see this. There's a certain rightness to this force. That's what we would call its x component, right? And there's a certain upness to this force. That's what we would call its y component. Now, both of these things are happening, right? As we pull it 60 newtons up and to the right, we're pulling it with some force to the right and some force up. How can we figure out how much of that force is to the right or up? Well, with trigonometry, right? To find the x component. The x component is the adjacent side. The force we know is the hypotenuse. So adjacent, hypotenuse, we can use cosine, right? The cosine of our angle will equal adjacent, the x component, over hypotenuse, 60 newtons. Okay, and we can solve this for fx. It's being divided by 60, so multiply both sides by 60. And we get that the x component, the rightness of this force, is 59.0885 newtons. So that's like a very good chunk of the 60, which actually makes sense because 10 degrees is a very small angle, right? It's mostly righty with a little bit of uppy thrown in, right? Okay, what about the y component? Well, y is opposite. Hypotenuse is still 60. Opposite hypotenuse, sine, right? So katoa. So very similar setup, except with sine instead of cosine, right? And we have 60 newtons times the sine of 10 degrees. To get that the y component of this force is only going to be 10.4189 newtons. Okay, so applying a force of 60 newtons at this angle produces the same result as applying this force to the right and this force up simultaneously. Okay, so I haven't done my sig digs there, I guess, because this is my final answer. So this should just be to 2 sig digs, 60 newtons, and this one, 10 newtons. All right. So I encourage you, pause the video, try this one on your own to remind yourself of how this works before I do it. But here we go. A force of 45 newtons acts at 200 degrees. Well, first of all, let's figure out what actually 200 degrees looks like, right? That means, again, we always start there, positive x-axis, and then counterclockwise, 0, 90, 180, and then 270, 360 would be all the way around, right? So we are at 200 degrees. So that means we are going counterclockwise. We're past 180, but we're not at 270, right? So our force is pointed something like that, downy lefty. Okay, but we can't make a triangle with that 200-degree angle, right? We've got to think about, okay, how do I now draw my triangle with its x and its y components? You got a couple options here. You could say, all right, we went 20 degrees past 180, right? So this angle here would be 20 degrees. You could also say we stopped 70 degrees short of 270, right? You could also look at it that way. This is 70. Both are totally valid, right? It just is going to mean when I sine, you cos. When you cos, I sine, right? We'll just have those backwards. I'm going to choose to go with the 20-degree one, okay? So I'm going to say that, actually, you know what? Let's mix it up. I'm going to go with the 70-degree one. So I'm going to choose to draw my triangle. When I go to do the components, I'm going to think of it this way. I'm going to say it's got a y component that's down, right? That's how much it's pushing downwards. I'll call it Fy. And then it's got an x component that's pushing to the left. That's Fx, okay? And for me, the way I've set it up, I'm going to look at that angle there and say, okay, that's 70 degrees, right? Reference to the vertical, that would be 70 degrees. And now we just use trigonometry to figure out what is the x component and the y component. So for x, now we've got opposite and hypotenuse. So for x, we'll do sine. Sine of 70 equals Fx over 45. And therefore, the x component of this force, right, the leftness, how hard it's pushing just to the left, I'm getting 42.2862 newtons. Okay, so 45 newtons at that angle means that to the left, it's feeling that much force. Repeat this now for the y component, but now y is adjacent. Hypotenuse is 45, so we'll use adjacent hypotenuse. That'll work with cosine, giving me that the y component is 15.3909 newtons. Okay, and that would be downward, which actually I did forget to do with my other ones here as well. So let's add direction, right? The x component to 2 sig digs would be 42 newtons. And what's the direction of the x component? Well, 180, right? It's purely to the left. That's the horizontalness of our force. And for the y component here, it's towards the bottom of the page, right? That's our 270. So 15 newtons at an angle of 270 degrees for the y component. I forgot directions on my components for this one. So for this one, the x component would be at 0 degrees, right? Perfectly to the right. And the y component is straight up. That would be 90 degrees. Okay, so let's think about this here. How could this person more effectively move the dog sideways, but not have to pull any harder? So what do you think? Pause the video, think about that for a sec, right? If they can't pull any harder, it means their force, the force itself, is kind of locked in, right? We don't want to make it any bigger. So how can we make it so that we more effectively move them sideways? Well, to make them move sideways, we want to be pulling as much sideways as possible, right? So if right now we're doing this, well, then our x component looks something like that, and our y component looks something like that, right? This y component, is that doing anything to move the dog sideways? No, right? That's trying to pull them up. That's kind of a waste of force if you want it to go sideways, right? So how could we change this without making our force itself any larger? How could we make this x component larger? Because that's what we want. We want to pull the dog harder sideways, not up, right? Well, what if we changed our angle? So instead of pulling up and to the right as much, what if, I'm going to try to draw it the exact same size, right? What if now we still pulled with the same force, but at a much smaller angle? Look at that. Look how much bigger our x component is now, right? Now, just by making the angle smaller, we've taken some of our force, right, that was kind of being wasted in the y-axis, and more of it is in the x-axis. Again, it's still the same force, right? Maybe it's 50 newtons, 50 newtons. It's not like the person got any stronger, but they're applying the force more effectively. So by decreasing that angle, you get more force in the x-axis. I mean, try this out for yourself with like a calculator on your table or something, right? If you want to move it sideways, push it sideways, right? If you try now pushing down and into the table while moving it sideways, you'll notice that it's a lot harder to move it because a lot of your force is being wasted in the y-axis where you're not actually trying to move it. Okay? All right. Let's try out some, same skills, same ideas, just getting a little more complicated with it now with this two-dimensional stuff. So another example, if we assume a constant velocity, now pause right there, very important. What did we just learn about the forces? Right, the net force needs to be 0 if it's got a constant velocity because that means the acceleration is 0. Right? The only way for the acceleration to be 0 is if the total force is also 0. They're asking us then, what is the magnitude of the force of friction? Okay, so we already said this here. Okay, what does this mean for the net force? If it's not accelerating, F net is 0. So like I said, physics is all about taking a simple idea and applying it in a million different ways. So right off the bat, I know that at some point in this calculation, right, we're pulling it to the right, it looks like, right, and it's not accelerating. So I know that that means F net x equals 0, and I know that it means F net y has to equal 0, right? If there's no net acceleration, there can be no net force. Okay, so those are the basic ideas. I know I'm going to be doing something where I'm going to add up all the x forces and they have to equal 0. Maybe that will let me find an unknown force, right? Same goes in the y-axis. Okay, we can answer this right off the bat. Which of Newton's laws applies here? If it's not accelerating, this is his first law. If F net is 0, acceleration will be 0. Okay. Now, let's go ahead and draw some diagrams here, okay? We will do some algebraic analysis, but always a good idea to set ourselves up for success with some diagrams. They've kind of given us the representational, but let's draw our free body to simplify things a bit. We've got two tractors pulling, so I'm just going to call them F1 and F2. And they're actually pulling with the same force, different directions, but same magnitude. Magnitude of 10,000 newtons. Okay, we're looking at this from above. So in this case, we can kind of just leave out the force of gravity because that would kind of be like down into the page, right? And the normal force, we know it's not accelerating in that axis anyway, so we're looking at this from above. Okay, so from our free body diagram here, right, we can tell we're missing something. We're missing a force, right? Because if I stopped here, this thing should be accelerating, right? We've got these two forces that are pulling to the right. Yes, also up and also down towards the bottom of the page, but they're both pushing right. So this couldn't be true. And we know this is true because it's not accelerating, right? So sometimes you catch stuff like that. You say, hang on, this thing would be accelerating, and it lets you, you realize, aha, right, there's friction here. So we know there's some force of friction pulling against those two forces. Now, how big is it? Well, you might think I've drawn it a little too big there, right? But don't forget, we have two forces here pulling to the right. So this force of friction needs to cancel out both x components here in order for the net x force to be 0, right? On our free body diagram, we can even add in our x components there, right? That would be F1x. And there's its y component, right? And F2x, same direction, same size, because the force itself is the same and the angles are the same, right? That would be F2's x component. And there's its y component, right? So I've drawn this force of friction to be roughly as large as both of these x components because it needs to be in order for them to be canceling out and give us 0. I actually did maybe draw it a little too big. Okay, but something like that. And again, we're told that this angle is 30 degrees and this angle is 30 degrees. So we can start to see, what we're going to do with this, right? We know we have everything we need to find these x components because we have the forces and the angles. And we know that together they have to be as big as the force of friction, right? If we draw our vector addition diagram, we've got F1 tip to tail with F2, and we know the next force to add in is our force of friction, and it has to bring us back to 0. Whoops, I went a little wonky there, right? Something like that, so that there is no net force. And sure enough, look at that, right? The x-ness of F1 and the x-ness of F2 have to be canceling each other out if we're going to get, have to be canceling with the force of friction if we're going to get a net force of 0, which we know we have because it's not accelerating. Their y components are also just canceling each other out. F1y is just as big up as F2y is down. So those just cancel each other out, okay, because of the geometry going on here. So we're always going to apply simple ideas. I find where students get in trouble here is they try to do everything all at once and jump to some big equation, right? We're never going to do that. Physics is about taking a simple idea and applying it in a million different ways. So here, the simple idea we're going to apply is physics principle number 0, which is that if the net force is 0, right, or rather, if the acceleration is 0, then the net force is 0. So we can just say we know that F net x has to equal 0. That's going to be our starting point here. And now we can get more specific. We can say, okay, well, what is F net x? It's the sum of all the forces in the x-axis. So for us, that means the force of friction is in the x-axis, and then force 1 has an x component, and so does force 2, right? Together, those all have to equal 0. We might need to go look in the y-axis later, but since we're just looking for the force of friction now, that's not a bad starting point, right? In fact, we might not even need to bother with the y-axis here because we have what we need to find F1x, and we have what we need to find F2x, which means the only thing we don't know is the thing we're trying to find, and therefore we can solve for it, right? I mean, we can see here, look, the force of friction, if I subtract F1x and F2x from both sides, must just equal this, right? And again, we can find both of those with trigonometry. And look at the physics speaking to us through the math here, right? Look what we're saying. We're saying the force of friction is going to be just as big as F1x and F2x, but in the opposite direction, right? As big as both of them together, but negative. Well, that's exactly what we said. It has to be just as big to the left as both of these together are to the right. Pretty cool. Okay, so to get those x components, let's use some trigonometry. I'm going to go pretty quick here because we just got some practice with that. So the cosine of 30 will equal the x component over the force itself, 10,000 newtons. And therefore, the x component of our force is going to be 8,660.2540 newtons. And you can hopefully see that it'll be the same. F1x is the same as F2x, right? They both have the 30-degree angle there and the 10,000 newtons, and that's adjacent. So that will be the same as F2x. And look at that. We now know this. We now know this. We should be able to just plug in and solve for the force of friction. Don't forget, though, we need to be very careful whenever adding vectors, which is what we're doing here, right? F net x is the result of adding every x component force, right? So we need to be careful to define our directions. I'm going to call right positive, left negative, and let's see what happens. That means that our force of friction is going to equal, okay, this negative is part of the equation, so negative F1's x component is to the right, so positive this number. Same goes for F2's x component, right? So putting those both in as positives because they're to the right, and then we have these negatives from rearranging our equation, I get that the force of friction is just going to be negative 17,320.508 newtons. Okay, so our negative means what? Well, it means to the left, right? Resisting how these were pulling it. That makes sense, so that's a good sign, right? And we can even see it, yeah, it's roughly, I mean, not even roughly, we can see the math there. It's double one of these components because the force of friction has to be just as big as both of these components together in order for the acceleration to be 0. So there we go. We got it. Our force of friction is going to be, and I get 5 significant digits here because I used the 10,000 newtons, and that's the only number I really needed here besides the angle. So 17,321 newtons. And for direction, we could say, 180 degrees based on how we've drawn it. Or we could even just say, it's okay to say directions like against motion, right? Be descriptive. Okay, I wouldn't say something like west because you don't actually know if that's west, right? How it was drawn. But there we go. Okay, so I want to emphasize here, I didn't know that we were jumping straight to something like this, right? And I'm a physics teacher. I started with the basic idea, and so should you. So keep that in mind as we go throughout this unit and throughout physics, okay? Start with a simple idea. F net has to equal 0 if it's not accelerating. Then you can break it down. What is F net? It's the sum of all the forces. If it's F net x, the sum of all the forces in the x-axis. So that has to equal 0, right? And then we can solve for what we don't know. Okay, and so the last few examples here, nothing new in terms of concepts. They're just some hanging sign problems, which are ultimately just another application of Newton's first law. So we're looking at things like this, where we have a sign or some structure being hung up. Okay, now, if all went well and we hung it properly, the sign should not be accelerating, right? Otherwise, it's not good. It's falling or it's moving in a way it shouldn't be, right? It's a hanging sign. So, if the signs are never accelerating, what do we automatically know about the net force that's acting on them? Right, it needs to be 0. And if the net force is 0, well, that means that F net x has to be 0, right? Otherwise, how could the net force be 0 if there's a net force horizontally? And similarly, that means F net y needs to be 0, right? Both components need to be 0 if the net force is going to be 0. This is going to be your starting point for any question where you know the net force is 0 because it's not accelerating, right? But definitely for hanging sign problems. Students so often say to me like, oh my goodness, there's a lot going on here. I don't know where to start. And the answer is always the same. Start with the fact that F net x has to equal 0 and F net y has to equal 0. Adding up all of the x components will equal 0. Adding up all of the y components will equal 0. Then you can go in and actually see what your x and y components are. So let's try a guided example here where it's going to walk us through step by step. It tells us that this sign's mass is 250 kilograms. So what must be the tensile strength of the chain and the minimum strength of the supporting bar? So what's the force of tension that the chain must need and the strength of this supporting bar here? So what's the force that's able to take? So in physics, again, it's always best to start with basic statements that we know to be true. So like we said, it's not accelerating. So we know, before even really diving in too hard, we know that F net is 0, and therefore both the x and the y components of the net force have to be 0. Okay, now we can start to break it down. We can think, okay, so what is F net x? Well, we add up the x components of every force, right? What is F net y? We add up the y components of every force, okay? Now, in order to do that, we're going to have to think a little bit more about what forces are involved here. So here's where we can start thinking about our actual forces and the diagrams and all that good stuff. All right, well, the sign has mass, so there is a force of gravity pulling down on it, right? What's more, we even know how to find that. It's mass times acceleration due to gravity, right? Mass times 9.81. Okay, now obviously that can't be the only force acting on it, or it would just be falling. But we can see, well, there must be, like, this tension in the chain is holding it up, right? We have a downward force, so there must be something with an upward component. And sure enough, that tension in the chain would have an upward component. Now again, that still can't quite be it, right? Because sure, we could say the upness of this cancels with the downness of this, but this also has a leftward component. So there's nothing right now to cancel with that. But then we look over here and we see, aha, because of this support bar, which is anchored to the wall, they're in contact, there would be a normal force there supporting against it, right? And so we've got this tension pulling up and to the left, the normal force pushing to the right, and the force of gravity pulling down. These forces must all be in equilibrium with each other so that the net force is zero. Let's visualize with some free body and vector addition diagrams. So for free body, we've got the normal force to the right, okay? We've got gravity pulling straight down. And then for our force of tension, it's up at an angle like this, okay? And we can start thinking about that tension's components. We're gonna have to, right? We can see that it's got an x component, and notice I've drawn it so that F tension's x component is just as big as the normal force, but in the opposite direction. It has to be, otherwise there would not be a net force of zero. They need to cancel each other out. Similarly, it also can't have a net y component. So however much gravity is pulling down, tension needs to be pulling up so that there's no net force in the y-axis either. And we even know that this angle here is 30 degrees. So we can add some information to our free body diagram that can help us out later, right? For our vector addition diagram, once again, the net force needs to be zero. So tip to tail, I've got Ft, Fg, and then that normal force needs to bring us back to where we started our diagram because we know the net force is zero, right? And you can see it in action here. The y component of Ft is just as big as Fg, but up. The x component is just as big as Fn, but left, so that they cancel each other out. Okay, so we started to got the picture here now, right? We know that F net x is zero. Well, once again, what is F net x? It's the result of adding up every x component. Now that we've done some work here, we can see that that just means F net x equaling zero means that, well, what are my x components? The normal force and tension's x component. So F normal plus Ft's x component has to equal zero. Started simple with the basic idea and then got specific to my problem. F net x had to equal zero or it would be accelerating horizontally. Well, F net x is just the normal force plus tension's x component. So that has to equal zero. Let's do the same in the y-axis. What is contributing to F net y? Well, force of gravity is in the y-axis, and so is the force of tension's y component. So the force of gravity plus the force of tension's y component has to equal zero, right? We've got these two equations. Now, do we have enough information in either of these equations to maybe find an unknown? Well, in this equation, we don't know the force of tension's x component. We also don't know the normal force. But in this equation, we know that the force of gravity is actually just mass times acceleration due to gravity. And we know the sign's mass is 250 kilograms. We know g is 9.81. So we actually do know this, which means we can find the force of tension's y component. Once we've got its y component, we'll know one side of the triangle and an angle, so you can see we're starting to get somewhere. Okay, but let's start there. Let's use, in step one, we're going to use this fact to find the force of tension's y component. Remember, ultimately what we're trying to find is Ft. So we're going to find the force of tension's y component by using this fact, what we just said. So by subtracting Fg from both sides, we can see that Fty equals negative Fg. Hey, once again, the physics speaks to us through the math, right? What did we say? However hard gravity is pulling down, tension needs to be pulling up, right? So same magnitude, but opposite directions, opposite signs. That reminds me, before I go any further, I better make sure I define my negative and positive directions, okay? Now, the force of gravity is just mass times acceleration due to gravity, right? So we're ready to go here. The force of tension in the y-axis is just going to be negative. The sign had a mass of 250 kilograms, they told us, and acceleration due to gravity is 9.81 meters per second squared, but down. So I'll put in a negative 9.81 meters per second squared. So doing that, I got that the tension's y component would be positive 2,452.5 newtons. Now our positive means that it's up, which makes a lot of sense because we said it had to be up in order to be canceling out the force of gravity, right? So there we go. We've got our tension's y component. Let's return to our free body diagram and think about what that means, right? I now know that this is 2,452.5. I know that this angle is 30. I'm trying to find the tension itself. So I want hypotenuse, I have opposite, and I have the angle. So I can actually just go ahead then and find the force of tension with some trigonometry, right? We just have this scenario here, right? Opposite over hypotenuse. So the sine of 30 degrees will equal opposite, the component we just found, over hypotenuse, the force of tension itself, right? The only thing we don't know in this equation is what we're trying to find. So we can solve for it. All right now it's in the denominator, so we need to get it out of there, right? Multiply both sides by ft. And there we go, we got it out of the denominator, but now it's being multiplied by the sine of 30, so divide both sides by the sine of 30. And then dividing our y component by sine 30, I got that the force of tension, this looks rounded, but it's actually not, is 4,905 newtons. Okay, so there we go. Just by using the fact that the net force in the y-axis had to be 0, along with a little bit of trigonometry, we were able to find what that force of tension must be. Now, I only get 3 sig digs here, so I'm going to have to use scientific notation. So to 3 significant digits, decimals here, 1, 2, 3, 4.9, and I would round that 0 to a 1 times 10 to the power of 3 newtons. For the direction of this force, we can't just say 30 because remember that would mean starting from 0 to 90. 30 would mean it's like that. But if this is 0, right, we can say that the direction is 180 minus 30, so 150 degrees. Okay, I guess it didn't actually ask us for direction because it just said what's the tension the chain needs to be able to withstand. And there's our answer, right? The chain needs to be able to support this sign, a minimum tensile strength of 4.91 times 10 to the 3 newtons. This is the type of calculation that engineers are doing all the time, right? If you're building a structure, you need to figure out how strong your materials need to be to support that structure. And then, of course, you add in a little wiggle room just to be safe, okay? All right, so there's part A done. We found the tensile strength. Part B is saying the minimum strength of the supporting bar. Well, what force does the supporting bar have to take? It has to be able to handle this normal force, right? And so where are we going to find the normal force? Well, by looking in the x-axis, right? And now we might not have ftx just yet, but we do have ft itself, right? So we can get its x component, and therefore the only thing we won't know will be the normal force, and we can solve for it. So once again, the physics speaks to us through the math here, right? Rearranging our force equation, we get that the normal force has to be just as big as tension's x component, but in the opposite direction. That's what we've said from the very beginning, because they need to cancel each other out. Okay, so let's get that x component. I mean, our diagram can help us out here again, right? We now know that this hypotenuse is 4,905. Okay, we could also use opposite. So let's go ahead and use some trigonometry to find ftx. So just using cosine in this case, you've actually got options. You could use tan. You could even use Pythagorean theorem since you know two sides. But I got that the x component would need to be 4247.8546 newtons. Now that's to the left side there, right? That's towards 180, which don't forget, we're calling negative in the x-axis. But now I've got that, I can go ahead, come down here and say that that means our normal force, which the bar must be able to handle, is going to be negative 4247.8546 newtons. And therefore, the normal force must be that many newtons, but to the right, right? However hard tension was pulling to the left, that normal force needs to be pushing to the right to give us a net force of 0. So, to 3 significant digits, we would write 4.25 times 10 to the power of 3 newtons. Okay, again, we don't really need direction here because they were just asking about how big is the force it needs to be able to handle, but it would be, it's to the right, we could say 0 degrees. Okay, so there we go. That is the normal force that that bar needs to be able to handle. So again, folks, I can't emphasize enough, we're starting simple. If it's not accelerating vertically, F net y is 0. If it's not accelerating horizontally, F net x is 0. Then you break down F net y into the sum of all y forces and solve for what you don't know if you can, right? Do the same in the x, okay? And take it nice and simple to begin with, and then you get more specific to your problem as you go. Notice how helpful our diagrams came in as we worked through that as well. Okay, last one here. All right. So now it's asking us, what is the tension in each rope if the sign has a mass of 150 kilograms? Okay, so again, what do we know for sure? We know that the net force in each axis has to be 0, right? So now to do something with this, we need to figure out what forces contribute to F net x and what contribute to F net y. So let's take a look at our scenario here. Again, it's a sign, it has mass, so there is going to be a force of gravity pulling straight downwards. And we know the sign's mass, so we basically have its force of gravity, right? It's just going to be 150 kilograms times 9.81. Okay, so there's this downward force. Why isn't it falling? Well, there needs to be some upward force, right? In order for this to be true, there needs to be some upward force. And we can see here that it's just these two wires holding it in place, right? Or rope, okay? So there's a force of tension from this one off at an angle and a force of tension from this one off at actually the exact same angle. And we can see here, right, again, whatever this thing's y component and this thing's y component, together, they need to exactly cancel out the force of gravity, right? And for the x components, well, we can see this is pulling to the right. This needs to be pulling just as hard to the left, okay? And because these angles are the exact same, that actually makes our lives kind of easy here because we know that this tension and this tension need to be the exact same. Otherwise, their x components couldn't be the same because of the fact that they're at the same angle. If the angles were different, it wouldn't be quite so simple. But because the angles are the same, the hypotenuse needs to be the same in order for the x components to be the same. And therefore, the y components also need to be the same. Okay, so it looks like we have more information in the y-axis. So I'm going to start there. Okay, I'm going to start by looking in the y-axis. First, let's just draw our diagrams to get our bearings here. For our free body diagram, we've got a force of gravity pulling down, and then two forces of tension pulling at angles. And again, we can see that their x components need to be canceling each other out, and then together, their y components need to be canceling out this force of gravity. However hard this is pulling down, these two together are pulling up. For our vector addition diagram, tip to tail, F tension 1 and F tension 2, plus the force of gravity brings us right back to where we started, which is what we expected, no net force, right? Okay, so like I said, we know a little bit more in the y-axis because we can get the force of gravity, right? We might think to look in the x-axis, but pretty quick we'd realize, well, I don't know anything in the x-axis, right? So let's start with the y-axis and see where it takes us. Start simple with the basic physics principle. If it's not accelerating, F net has to be 0, right? Physics principle number 0. So what is F net y? What contributes to F net y? Well, we've got Fg, the y component of the first tension, and the y component of the second tension. So add those up, they have to equal 0. Okay, now, here's where the fact that we know they have to be the same comes in handy, right? Because they have the same angle, and they need to have the same x component to cancel each other out, we know they also need to have the same y components, right? So ft1y and ft2y are actually the same number, which means we can just combine them like they're like terms. I'm just going to say, since the y component of the first tension has to be the same as the y component of the second tension, they're the same number, I'm just going to call them fty, right? So we really just have one fty plus another of the same number, okay? Which means we can combine them and just say fg plus 2 FTY has to equal 0. Now again, we basically know this. We just have to multiply the mass by 9.81. So let's rearrange for FTY. I'm going to subtract FG from both sides. And then divide both sides by 2. And that gives us kind of an interesting idea that we could have predicted, right? Look, it's saying each Y component is just sharing half of the force of gravity. They're both supporting against gravity. They both have to support half of it. Fg over 2. Now we know Fg is again just mass times acceleration due to gravity. So negative Fg over 2 becomes negative mg over 2, where g is 9.81. Okay, now we're about to put numbers in, so if we didn't already, we definitely need to now make sure we define our directions. Up is positive, down is negative. Little way we can make predictions and check our work. We are hoping we get a positive answer here because we know the y components of the tension needed to be upwards. Let's put in our numbers. We know the mass is 150 kilograms and acceleration due to gravity is 9.81 meters per second squared, but downwards. So I'm going to do negative 9.81 meters per second squared. Those double negatives will cancel and give us a positive. That's good, right? We were hoping for a positive. So I got that the force of tension in the y-axis for each of our two ropes is 735.75 newtons, right? Up. Okay, so that is, for both of these triangles, that is this side here, right? Now be careful, we didn't want just the vertical component of the tension, we wanted the tension itself. But now we know, right? We know this angle is 27.4 degrees in here or in here, right? We have opposite. We just want hypotenuse, the tension itself. So let's go ahead and get that. I'll use tension 2 for my little diagram here, but it'll be the same for tension 1, just in a different direction, okay? We know that side is 735. We know this angle is 27.4 degrees. So how can we get the tension itself? Well, that's hypotenuse. We have opposite. So opposite hypotenuse, we can use sine here. Opposite over hypotenuse. So let's rearrange this for Ft2. It's in the denominator. So if we multiply both sides by force of tension 2, and then divide both sides by sine of 27.4, we can solve for the force of tension being 1,598.7622 newtons. Okay, so all that's left now, we know it'll be the same for the other side for force of tension 1. The difference will just be in the direction, okay? So for force of tension 2, it's easy, right? We got 0, we got 90. Well, look, as we go counterclockwise, we're trying to communicate that direction. That one's just going to be at 27.4 degrees. For Ft1, though, we got to think a little bit more because that angle is 27.4 degrees, right? We can't just say that or people will think we mean this direction, but we can say, okay, as we go counterclockwise, what would that angle there be? Well, this is 180, right? And we are 27.4 degrees short of the full 180. So this angle here is just going to be, I got 152.6 degrees. Okay, so there we go. All that's left now is SIGDIG's direction, recording our answer. So we get 3 significant digits. So for Ft2, we're going to have to use scientific notation. This is going to be 1.60 times 10 to the power of 3 newtons at an angle of 27.4 degrees. Okay, for Ft1, exact same magnitude, just a different direction. Ft1 is off at an angle of 152.6 degrees. For my SIGDIGs on my angles there, I'm just following the general rule that use the same number of decimal places you were given for the angle. So there we go. Those are the 2 forces of tension. All right, but notice again, we started simple. We said we know the net force in the y-axis has to be 0. We know that the net force in the y-axis is just the result of adding up all the forces y components, right? And then we solved for the one thing we didn't know in that equation, right? Then some trigonometry got us what we wanted. All right, so that wraps up the notes and examples for the first lesson of Unit B in Chapter 3, okay? Go ahead and start out with this one, which is a hanging sign problem, but then you are able to do the rest of the practice problems for this lesson, okay? As always, don't hesitate to reach out for help or questions or anything as you go, okay? I'm always here to help, but there we go. Unit B has begun. We are done the first lesson.